Here's something that will blow your mind. If you could count every star in our galaxy alone, you'd reach 400 billion before you even started on the roughly 2 trillion other galaxies scattered across the observable universe. Current estimates place the total number of stars at around 200 billion trillion throughout all of space. With all those blazing suns radiating light in every direction, logic says the night sky should be as bright as daylight. Yet when you look up at night, you see mostly darkness. This contradiction stumped astronomers for over 400 years until recent discoveries from the James Webb Space Telescope finally revealed the shocking truth about why our universe remains dark. The fundamental mystery that stumped scientists. This contradiction forms the foundation of what astronomers call Olbers Paradox, named after Heinrich Olbers, who formalized the problem in 1823. The mathematical logic appears unbreakable. If the universe extends infinitely in all directions and contains a uniform distribution of stars, then every line of sight from Earth should eventually intersect with the stellar surface. This means the entire night sky should glow with the combined brightness of all those stellar surfaces, creating a luminosity comparable to staring directly at the sun's photosphere. Johannes Kepler first recognized this astronomical puzzle in the early 1600s when he observed that the darkness of night seemed to contradict the infinite universe model that many scholars accepted. Kepler reasoned that if space truly contained endless stars stretching to infinity, the accumulated light from all those distant suns should make nighttime as brilliant as day. The fact that darkness dominated the night sky led Kepler to conclude that the universe must have boundaries, with a finite number of stars distributed across a limited volume of space. Yet Kepler's finite universe solution created its own problems. If stars existed only within a bounded region of space, what lay beyond those boundaries? The concept of an edge to the universe raised uncomfortable questions about what might exist in the void beyond the stellar realm. These philosophical implications troubled scientists who preferred elegant, unbounded cosmic models that avoided arbitrary limits on the universe's extent. The paradox gained renewed attention during the 19th century as telescopes revealed ever more distant stars and nebulae. Each improvement in observational technology uncovered additional layers of cosmic structure, suggesting that the universe contained far more luminous objects than previously imagined. Heinrich Olbers approached the problem with mathematical rigor, demonstrating that even accounting for the inverse square law of light intensity, an infinite universe with uniformly distributed stars would still produce a blindingly bright night sky. Olbers calculated that while individual distant stars contribute less light due to their remoteness, the sheer number of stars at each distant shell would compensate for this dimming effect. In an infinite universe, the number of stars within successive spherical shells increases as the square of the radius, exactly canceling out the inverse square reduction in brightness from each individual star. This mathematical relationship meant that stars at every distance would contribute equally to the total sky brightness, making the darkness of night theoretically impossible. Several 19th century scientists proposed solutions involving interstellar dust that might absorb starlight before it reached Earth. They suggested that cosmic dust clouds scattered throughout space could block the light from distant stars, explaining why the night sky remained dark despite containing countless luminous objects. However, this dust absorption hypothesis contained a fatal flaw. Any material capable of absorbing enough starlight to darken the night sky would eventually heat up and begin glowing itself, ultimately contributing its own thermal radiation to the cosmic brightness. The paradox challenged fundamental assumptions about the nature of space, time, and cosmic structure. If the universe truly extended infinitely and had existed for an infinite duration, then light from every possible stellar source should have had sufficient time to reach Earth. The mathematics suggested that under these conditions, the night sky should shine with an intensity of approximately 200,000 times brighter than the full moon, creating perpetual daylight conditions across Earth's surface. Early 20th century astronomers began recognizing that the darkness paradox might reveal something profound about cosmic evolution and structure. The problem forced scientists to question whether their basic assumptions about the universe's properties might be fundamentally incorrect. Perhaps the universe was not infinite in extent, or maybe it had not existed for an infinite duration, or possibly the distribution of stars was not as uniform as previously assumed. The stakes of solving this paradox extended far beyond academic curiosity. The darkness of night touched on fundamental questions about the origin, evolution, and ultimate fate of the universe itself. If scientists could understand why space appeared dark, despite containing enormous numbers of luminous objects, they might unlock secrets about the cosmic timeline, the universe's geometry, and the physical laws governing light propagation across vast distances. The paradox also connects to everyday human experience in profound ways. Every person who has ever looked up at a star-filled night has witnessed this cosmic mystery firsthand. The sense of awe and wonder that darkness evokes stems partly from the subconscious recognition that something about the night sky defies our intuitive expectations. Our brains evolved to associate brightness with safety and darkness with potential danger, making the cosmic darkness feel both beautiful and slightly unsettling. Current research suggests that solving Olbers Paradox requires understanding multiple interconnected phenomena that were unknown to 19th century astronomers. The expansion of space itself affects how light propagates across cosmic distances, while the finite age of the universe limits how much light has had time to reach any given observation point. Additionally, the universe's structure is far from uniform, with matter concentrated into galaxies and galaxy clusters separated by vast empty regions. The paradox ultimately revealed that the universe possesses a hidden architecture that completely contradicts our intuitive assumptions about cosmic brightness. To understand why this cosmic darkness persists, we need to examine how light behaves in our own immediate environment and compare it to the vast emptiness of space. How Earth creates its brilliant daylight. Consider how Earth transforms a single star's light into the brilliant daylight that illuminates our world from horizon to horizon. The sun represents just one ordinary star among the countless billions scattered throughout the galaxy, yet during daytime hours it manages to flood our entire planet with radiant brightness. This remarkable transformation occurs not because our star possesses any special properties compared to distant suns, but because Earth possesses something that space completely lacks, an atmosphere packed with particles that redirect and amplify the incoming solar radiation. Our atmosphere contains approximately 78% nitrogen, 21% oxygen, and traces of other gases, along with countless microscopic particles including dust, water droplets, and aerosols suspended throughout the air column. These components create a dense medium that fundamentally alters how light behaves when it enters our atmospheric envelope. Every photon arriving from the sun encounters billions of these tiny obstacles during its journey through the air, causing the light to bounce and scatter in multiple directions rather than traveling in straight lines. Rayleigh scattering governs this atmospheric light redirection process. When sunlight encounters gas molecules and particles smaller than the wavelength of visible light, these tiny objects act as microscopic mirrors that deflect the incoming radiation. The effectiveness of this scattering depends directly on the wavelength of the light involved. Shorter wavelengths experience much stronger scattering than longer wavelengths, with blue light scattered approximately 10 times more effectively than red light. This wavelength-dependent scattering explains why our daytime sky appears blue rather than the white color of direct sunlight. Blue photons with wavelengths around 450 nanometers get bounced around the atmosphere so extensively that they seem to arrive from every direction simultaneously. Meanwhile, red photons with wavelengths near 650 nanometers pass through the atmosphere with minimal deflection, allowing them to maintain their original directional properties. The result creates the familiar blue dome that surrounds us during daylight hours. The atmosphere essentially functions as a vast network of light redistributors. Each gas molecule and particle acts as a tiny relay station that captures incoming solar radiation and broadcasts it in random directions. This process transforms the sun's parallel beam of light into a diffuse glow that illuminates the entire sky hemisphere. Without this scattering mechanism, we would see only a brilliant white disk of the sun against a completely black background, similar to what astronauts observe from space. Atmospheric particles redirect light with remarkable efficiency. A single photon might encounter hundreds of scattering events during its passage through the air column, getting bounced from molecule to molecule before finally reaching our eyes. This multiple scattering creates the soft, even illumination that characterizes terrestrial daylight. The light arriving at any location on Earth's surface includes both direct radiation from the sun and scattered radiation from all other directions, combining to produce the bright conditions we experience. The thickness of our atmospheric layer determines how extensively this scattering occurs. During midday, when the sun reaches its highest position, sunlight travels through the minimum amount of atmosphere, resulting in intense blue sky conditions. As the sun approaches the horizon during sunrise and sunset, light must traverse increasingly thick atmospheric layers. This extended path allows more scattering opportunities, causing shorter wavelengths to get deflected away while longer red and orange wavelengths continue toward the observer. Astronauts orbiting Earth witness a dramatically different visual environment that reveals how unusual our atmospheric light amplification really is. From space, the sun appears as an intensely bright point source against the absolute blackness of the cosmic void. Even with the sun shining directly on their spacecraft, astronauts see no diffuse sky glow whatsoever. The absence of atmospheric particles means that light travels in perfectly straight lines, creating stark contrasts between illuminated and shadowed regions. This atmospheric amplification effect theoretically should apply to starlight as well as sunlight. Every star in the night sky emits photons that enter our atmosphere and encounter the same gas molecules and particles that scatter solar radiation. The light from Sirius, Vega, and countless other stars should undergo Rayleigh scattering, just like sunlight does, creating diffuse glows that brighten the night sky. Yet, despite containing the same scattering mechanisms that create brilliant daylight, our atmosphere fails to transform starlight into significant sky brightness. Even on the clearest nights, far from artificial illumination, the scattered starlight contributes only a faint glow that remains barely detectable to human vision. This dramatic difference between the atmosphere's treatment of sunlight versus starlight hints at fundamental distinctions between our local star and the distant stellar population. The intensity difference between sunlight and starlight provides the crucial factor explaining this atmospheric amplification discrepancy. Our sun delivers approximately 1,360 watts of energy per square meter to Earth's upper atmosphere, creating an enormous flux of photons available for scattering. In contrast, even the brightest stars deliver less than 1/1,000,000th of this energy flux, providing far fewer photons for the atmospheric scattering process to redistribute. Our protective atmospheric envelope creates a localized bubble of enhanced brightness around Earth by capturing and redistributing the intense radiation from our nearby star. This process transforms what would otherwise be a single brilliant point of light into the diffuse, comfortable illumination that sustains life on our planet. However, this same atmosphere cannot perform similar brightening magic with the incredibly faint light arriving from distant stars scattered throughout space. The brilliant blue sky that surrounds us represents an artificial enhancement created by our planet's gaseous envelope, but this raises a profound question about what happens to light when it encounters the vast emptiness between the stars. The shocking emptiness of space. Space operates under completely different rules than our familiar atmospheric environment. The vacuum between stars contains fewer than 1 atom per cubic centimeter, creating conditions so empty that light rays travel for billions of years without encountering a single particle capable of redirecting their path. This extreme emptiness fundamentally changes how illumination behaves compared to the dense conditions that create Earth's bright daylight. The interstellar medium represents the closest thing to a perfect vacuum that exists in nature. Between stellar regions, particle density drops to levels that terrestrial laboratories struggle to replicate even with advanced vacuum technology. A cubic meter of space might contain fewer particles than exist in a single breath of Earth's atmosphere. This sparse distribution means that starlight encounters virtually no obstacles during its passage through the cosmic environment. Without scattering particles, light maintains its original directional properties throughout its journey across space. Photons travel in perfectly straight lines from their stellar sources without experiencing the random deflections that create atmospheric brightness on Earth. Each light ray maintains its precise trajectory, carrying energy in a narrow beam that only becomes visible when it directly enters an observer's eye or strikes a physical surface. The space between these light beams remains completely dark because no particles exist to redirect the energy toward other viewing angles. This directional nature of unscattered light explains why astronauts see only pinpoints of stellar brightness against an otherwise black background. Even when surrounded by intense starlight streaming in all directions, the space around them appears dark because their eyes detect only the photons traveling directly toward them. The countless light rays passing nearby remain invisible because nothing deflects them into the astronaut's line of sight. The contrast between Earth's atmospheric density and space's emptiness becomes apparent when comparing their particle concentrations. Our planet's atmosphere contains approximately 2.5 quintillion molecules per cubic centimeter at sea level, creating a dense medium that interacts extensively with incoming radiation. The interstellar medium averages less than 1 particle per cubic centimeter across most of its volume. This represents a density difference of more than 24 orders of magnitude, explaining why atmospheric scattering creates bright skies while space remains dark. Even regions that astronomers consider relatively dense still contain far too few particles to generate significant light scattering. The densest molecular clouds in the galaxy might reach concentrations of several million particles per cubic centimeter, which sounds impressive until compared to atmospheric densities. These supposedly dense cosmic regions still contain fewer particles than exist in the best laboratory vacuums on Earth, making them incapable of producing the scattering effects that brighten terrestrial skies. The concept that darkness represents the absence of scattering rather than the absence of light fundamentally changes how we understand cosmic illumination. Space contains enormous quantities of electromagnetic radiation streaming in all directions from countless stellar sources. This energy fills the cosmic volume, carrying power levels that would overwhelm any observer if concentrated into visible form. However, without particles to redirect and scatter this radiation, it remains invisible to anyone not positioned directly in its path. Consider the light streaming past Earth from distant galaxies at this very moment. Trillions of photons carry energy through the space around our planet, traveling on trajectories that will carry them to other regions of the universe. These light rays pass invisibly through the solar system because no scattering medium exists to make them visible. Only the tiny fraction of cosmic light that happens to travel directly toward Earth becomes detectable, while the vast majority continues its journey unseen through the empty space between celestial objects. This explains why adding more stars to the universe cannot solve the darkness problem through simple multiplication. Each additional star contributes its own beam of directed light, but these beams travel in straight lines without illuminating the space between them. 1 trillion stars produce 1 trillion separate light beams, but the dark regions between those beams remain just as dark as before. The emptiness of space ensures that increased stellar populations create more points of light rather than diffuse cosmic brightness. Cosmic dust plays a particularly important role in the limited scattering that does occur in space. These microscopic solid particles, composed primarily of silicates and carbon compounds, interact more effectively with light than individual gas molecules. Dust grains can absorb starlight and re-emit it at longer wavelengths, creating the faint infrared glow that space telescopes detect throughout the galaxy. Yet even in dust-rich regions of space, the particle density remains far too low to generate the bright, scattering effects that characterize planetary atmospheres. The straight-line propagation of light through empty space also means that stellar illumination decreases rapidly with distance from each source. Unlike atmospheric scattering that distributes light evenly across the sky, cosmic illumination follows strict geometric relationships that determine how much light reaches any given location. The mathematical precision of these distance relationships reveals another crucial factor that contributes to cosmic darkness: the mind-bending scale of stellar distances. These distance relationships become staggering when we examine our cosmic neighborhood in detail. Our nearest stellar neighbor beyond the Sun lies so far away that traveling there with our fastest current spacecraft would require more than 70,000 years of continuous flight. Proxima Centauri sits at a distance of 4.246 light-years from Earth, which translates to roughly 25 trillion miles of empty space, separating us from the closest star we could theoretically visit. This immense gap represents just the beginning of understanding how cosmic distances create the darkness that surrounds us each night. Within a sphere extending 50 light-years from our solar system, astronomers have cataloged approximately 2,000 individual stars. This count might seem substantial until you consider the volume of space involved. That sphere contains roughly 65,000 cubic light-years of mostly empty void, meaning each star occupies an average volume equivalent to about 32 cubic light-years of space around it. These measurements demonstrate that stars exist as isolated islands of light floating in an ocean of darkness. The average distance between neighboring stars and our galactic neighborhood measures approximately 5 light-years, though this spacing varies considerably in different regions. Some stellar pairs orbit much closer together, while vast stretches of space contain no stars whatsoever across distances spanning dozens of light-years. The overall pattern creates a three-dimensional network where bright points remain separated by enormous volumes of empty darkness. Light intensity follows the inverse square law with ruthless mathematical precision as it travels through these cosmic distances. When starlight spreads outward from its source, the energy disperses across increasingly larger spheres of space. A star located twice as far away delivers only 1/4 the light intensity to any observer. At 10 times the distance, the same star appears 100 times dimmer. This relationship means that even massive, luminous stars become nearly invisible when viewed across the typical distances that separate stellar objects. Consider Rigel, one of the most luminous stars visible in Earth's night sky. This blue supergiant generates approximately 120,000 times more light than our Sun, making it one of the most powerful stellar engines in our local galactic region. Yet Rigel appears as merely a bright dot to the naked eye because it lies roughly 860 light-years away. The inverse square law has reduced its tremendous luminosity to a tiny fraction of its original intensity by the time that light reaches Earth. If Rigel occupied the same position as our Sun, it would incinerate our planet with its overwhelming energy output. The mathematical relationship governing stellar brightness across cosmic distances ensures that only a handful of nearby stars contribute meaningful illumination to Earth's night sky. Stars beyond approximately 100 light-years become so dim that they blend in hard general background glow, regardless of their actual luminosity. Even if astronomers discovered a star 1 million times brighter than our Sun, placing it at a distance of 1,000 light-years would render it barely visible to human vision due to the relentless effects of distance dimming. These vast separations create enormous regions of space that receive virtually no starlight whatsoever. The darkness between stellar systems extends across light-years of empty void where no significant illumination exists to brighten the cosmic environment. Spacecraft traveling through interstellar space would experience conditions of almost perfect darkness, with only the faintest pinpricks of distant stars providing any visual reference points. Recent calculations reveal that adding billions more stars to our galaxy would not significantly improve the overall brightness of space. The fundamental problem lies not in the quantity of light sources, but in their distribution across the immense volume of cosmic space. Even if astronomers discovered 10 times more stars than currently known, those additional light sources would still remain separated by the same crushing distances that isolate existing stellar populations. The universe's structure resembles a sparse web rather than a continuous field of illumination. Galaxies themselves cluster into filamentary networks separated by vast voids containing virtually no luminous matter. Within each galaxy, stars concentrate into spiral arms and central bulges, but even these relatively dense regions maintain enormous empty spaces between individual stellar objects. The overall architecture creates a cosmic environment where light sources exist as rare exceptions within an overwhelming background of darkness. The concept of stellar magnitude provides a quantitative framework for understanding how distance affects perceived brightness. Each magnitude represents a factor of 2.5 difference in apparent luminosity, meaning that a magnitude 1 star appears 2.5 times brighter than a magnitude 2 star. The faintest stars visible to the naked eye reach magnitude 6, while most cosmic distances push stellar brightness well beyond this detection threshold. The vast majority of stars in the universe remain completely invisible to human vision due to their remote locations. Astronomers have calculated that concentrating all the stars in our galaxy into a much smaller volume would still fail to create uniform cosmic brightness. Even if stellar spacing decreased by a factor of 10, reducing average distances to less than 1 light year, the inverse square law would still ensure that most stars contributed negligible illumination to any given location. The universe operates as a collection of isolated light sources floating in an endless sea of darkness, where distance serves as the ultimate factor determining whether stellar illumination can overcome the overwhelming emptiness of space. Yet recent technological advances have begun revealing stellar populations that previous generations of astronomers never imagined existed, fundamentally changing our understanding of how many light sources actually populate the cosmic void. The James Webb Space Telescope has transformed our understanding of stellar populations through discoveries that surpass every previous astronomical survey. Since beginning operations in 2022, this revolutionary instrument has peered deeper into space and further back in time than any telescope before it, revealing stellar populations that existed when the universe was merely a fraction of its current age. The infrared sensitivity of Webb allows it to detect light that has been stretched by cosmic expansion from visible wavelengths into the infrared spectrum, making previously invisible stars suddenly accessible to detailed study. Webb's most remarkable achievement involves detecting individual stars across distances that were considered impossible to resolve just a few years ago. The telescope recently identified 44 individual stars in a galaxy located nearly 6.5 billion light-years from Earth, a feat accomplished through the combined power of gravitational lensing and Webb's unprecedented sensitivity. This galaxy, known as the Dragon Arc, exists in an era when the universe was only half its present age, allowing astronomers to study stellar populations from a time when cosmic star formation operated under dramatically different conditions than today. The Dragon Arc represents a mishmash of several duplicated images of a single background spiral galaxy, created by gravitational lensing as light passes around the massive Abell 370 galaxy cluster. This natural cosmic magnification effect amplifies the distant galaxy's light by factors of thousands, enabling Webb to resolve individual stellar objects that would otherwise remain completely undetectable. The colors of these newfound stars indicate they are red supergiants in the final stages of their lives, similar to Betelgeuse in our own cosmic neighborhood, providing direct evidence of stellar evolution processes operating in the early universe. These observations have revised our estimates of stellar populations throughout cosmic history. Previous surveys using ground-based telescopes and even the Hubble Space Telescope could only detect galaxies as unified blobs of light at such extreme distances. Webb's ability to resolve individual stars within these distant systems has revealed that early galaxies contain far more massive stars than astronomers previously suspected. The telescope has identified stellar populations with masses and luminosities that challenge existing models of early cosmic star formation. The updated stellar census data incorporates Webb's discoveries to produce dramatically revised estimates of star counts throughout the observable universe. Current calculations suggest our galaxy alone contains between 200 and 400 billion stars, while the observable universe holds approximately 200 billion trillion stars across its estimated 2 trillion galaxies. These numbers represent significant increases from previous estimates, which were based on less sensitive observational techniques that missed many stellar populations, particularly in the early universe. Webb has also revealed that many stars remain hidden from our view due to cosmic dust absorption and redshift effects. The telescope's infrared capabilities allow it to peer through dust clouds that completely block visible light, revealing stellar nurseries and mature stellar populations that were invisible to previous surveys. In some regions of space, Webb has discovered stellar populations that are 10 times more numerous than visible light observations suggested, indicating that earlier star counts significantly underestimated the true stellar content of the universe. The telescope has identified massive stellar populations in galaxies that formed when the universe was less than 1 billion years old. These early galaxies appear to contain surprisingly mature stellar systems with evidence of multiple generations of star formation and stellar death. The presence of heavy elements in these ancient stellar populations indicates that massive stars had already lived and died, enriching the cosmic medium with elements forged in stellar cores and distributed through supernova explosions. One particularly surprising discovery involves the detection of red supergiant stars in extremely distant galaxies. These evolved stellar objects represent the final phases of massive star evolution, indicating that the early universe experienced rapid stellar formation and evolution cycles. The identification of these stellar types at such early cosmic epochs suggests that star formation began much sooner after the Big Bang than previous models predicted. Webb's observations have also revealed unexpected stellar population characteristics in early galaxies. Many of these ancient stellar systems appear to contain higher proportions of massive stars than exist in contemporary galaxies. This top-heavy stellar mass distribution would have created much brighter early galaxies than astronomers expected, contributing more light to the cosmic background than previous calculations suggested. Despite these revolutionary discoveries that have dramatically increased our estimates of stellar populations, the fundamental darkness paradox remains unsolved. Adding trillions more stars to our cosmic inventory does not eliminate the darkness of space because these additional light sources still obey the same physical laws governing light propagation and intensity. The inverse square law continues to ensure that even the most luminous stellar populations contribute negligible brightness when viewed across cosmic distances. The improved stellar counts actually intensify the darkness paradox rather than resolving it. With more stars contributing light to the cosmic background, theoretical calculations predict that space should appear brighter than observations indicate. Webb's discovery of abundant early stellar populations means that the universe has been generating starlight for a longer period than previously thought, providing additional time for that light to accumulate and brighten the cosmic background. The revolutionary star counts provided by Webb have made the cosmic darkness paradox more puzzling rather than providing a solution. The abundance of stellar populations throughout cosmic history should theoretically create a brighter cosmic background than we observe. Yet the mathematics of stellar brightness and cosmic distances alone cannot explain why space remains dark despite containing such enormous numbers of luminous objects. The answer requires understanding a fundamental property of the universe itself that completely changes how we think about cosmic illumination: the universe's hidden time limit. This fundamental property reveals itself as time itself. The universe carries a secret that completely changes how we understand cosmic darkness. It simply hasn't existed long enough for light from every star to reach us. This finite age of approximately 13.8 billion years creates an invisible boundary in space called the cosmic horizon, beyond which no light has had sufficient time to complete its journey to Earth. Every photon we detect tonight began its travels within this cosmic time limit. while countless stars beyond this boundary remain forever invisible because their light still races through the darkness toward us. This temporal constraint means that when astronomers peer into the deepest regions of space, they encounter a fundamental limit imposed not by technology, but by physics itself. Light travels at a constant speed of roughly 186,000 miles per second, which sounds incredibly fast until measured against the immense distances separating cosmic objects. Even at this tremendous velocity, light requires substantial time to cross the gaps between stellar systems, galaxies, and galaxy clusters distributed throughout the universe. The concept of look-back time reveals how every astronomical observation becomes a journey through cosmic history. When we observe the Andromeda Galaxy, we see light that departed those distant stars approximately 2.5 million years ago, showing us how that galaxy appeared during Earth's Pliocene epoch when early human ancestors first walked across African landscapes. More distant objects show us progressively earlier chapters of cosmic evolution, with the most remote galaxies displaying conditions that existed when the universe was only a few hundred million years old. Current observations with advanced telescopes allow us to detect galaxies whose light began its journey when the universe was less than 400 million years old. These ancient stellar systems appear as they existed during the cosmic dawn, when the first generation of stars was just beginning to illuminate the primordial darkness. The light from even more distant objects continues traveling toward us through space, but those photons have not yet completed their multi-billion-year journeys to reach our solar system. This finite light travel time directly addresses the fundamental assumptions underlying the cosmic brightness paradox. The original formulation of this problem assumed that stars existed at all possible distances throughout an infinite universe, with their combined light eventually reaching every observation point. However, the universe's finite age restricts the volume of space from which we can receive starlight, creating a spherical boundary centered on Earth beyond which no objects remain visible regardless of their actual brightness or abundance. The observable universe encompasses only that region of space whose light has had time to reach us since the Big Bang occurred roughly 13.8 billion years ago. This cosmic sphere extends approximately 46.5 billion light years in all directions from Earth, accounting for the expansion of space that has occurred while light traveled toward us. Stars and galaxies beyond this boundary certainly exist, but their light has not yet crossed the enormous distances required to become part of our observable cosmic environment. An infinite universe containing uniformly distributed stars would indeed create the blazing night sky that early astronomers predicted, but only if that universe had existed for an infinite duration. The finite cosmic age prevents this scenario from occurring because insufficient time has passed for light from the most distant stellar populations to contribute to the brightness we observe. The darkness between stars reflects not the absence of distant light sources, but the absence of sufficient time for their illumination to reach us. The cosmic microwave background radiation represents the most ancient light detectable in the universe, originating from conditions that existed approximately 380,000 years after the Big Bang, when the universe first became transparent to electromagnetic radiation. This radiation has been traveling towards us for nearly the entire age of the universe, representing the ultimate limit of how far back in time our observations can penetrate. The first stars formed roughly 100 to 200 million years after the Big Bang, meaning their light has been traveling through space for approximately 13.6 to 13.7 billion years. These primordial stellar objects ended their lives long ago, but their light continues streaming through the cosmic void toward us. Some of this ancient starlight will reach Earth millions of years in the future, gradually adding to the cosmic background illumination that bathes our planet. The universe operates like a cosmic time machine where distance directly correlates with age. Objects located 10 billion light years away appear as they existed 10 billion years ago, when the universe was only 3.8 billion years old and contained far fewer mature stellar populations than exist today. The most distant galaxies observable with current technology show us cosmic conditions from when the universe was merely 400 million years old. representing just 3% of its current age. Recent calculations suggest that stars beyond approximately 13.8 billion light-years from Earth remain permanently invisible because their light has not had sufficient time to reach us since the universe began. These stellar populations certainly contribute to the cosmic light inventory, but their illumination travels through space toward observation points they may never reach. The darkness surrounding us represents compelling evidence of the universe's finite age, demonstrating that cosmic history operates within temporal constraints that limit how much stellar light can accumulate at any given location. Yet this temporal limitation represents only part of the cosmic darkness equation, as the very fabric of space itself actively works against the accumulation of starlight through processes that stretch and weaken the light during its journey across the expanding universe. Cosmic expansion's role in eternal darkness. This stretching process operates through mechanisms that fundamentally alter electromagnetic radiation as it crosses the expanding cosmos. When starlight travels through a universe that continuously grows larger with each passing moment, the expansion of space itself stretches the wavelengths of every photon during its journey across cosmic distances. This cosmic stretching process operates on such vast scales that it remains invisible in our daily experience, yet it profoundly influences every photon that reaches Earth from distant stellar sources. Cosmic expansion literally pulls apart the wavelengths of light traveling through space, causing photons to lose energy during their journeys across the universe. This wavelength stretching transforms the original colors emitted by distant stars into longer, redder wavelengths that carry less energy than when they began their cosmic voyages. The redshift phenomenon demonstrates how expansion affects stellar illumination in measurable ways, with light emitted at blue wavelengths from extremely distant galaxies getting stretched so extensively that it arrives at Earth as infrared radiation completely invisible to human eyes. This wavelength stretching reduces the apparent brightness of distant stars through a process entirely separate from the inverse square law that governs nearby stellar illumination. While the inverse square law reduces brightness due to geometric spreading of light across larger areas, redshift dimming occurs because individual photons lose energy as space expands around them. The combination of these two effects creates a double dimming that makes extremely distant stars appear far fainter than their actual luminosity would suggest. The most distant galaxies recede from us at velocities approaching the speed of light itself according to Hubble's law, which states that more remote objects move away faster than nearby ones. Galaxies located billions of light years away travel through space at such tremendous speeds that their light experiences extreme Doppler shifting in addition to the wavelength stretching caused by spatial expansion. The most distant observable galaxies recede at velocities exceeding 90% of light speed, creating redshift values that push their originally visible light far into the infrared spectrum. Stars that emit brilliant blue and white light in these remote systems appear only as faint infrared sources when observed from Earth. The energy contained in their photons has been reduced by factors of 10 or more during the cosmic journey, dramatically diminishing their contribution to the brightness of our night sky. This light-stealing effect intensifies over cosmic time as the expansion of the universe accelerates under the influence of dark energy. Current observations indicate that cosmic expansion began accelerating approximately 5 billion years ago, meaning that photons emitted since that time have experienced increasingly severe redshift dimming. Dark energy drives this acceleration by exerting a repulsive force that overwhelms gravitational attraction on the largest cosmic scales. As dark energy dominates the universe's dynamics, it causes space to expand ever-increasing rates, creating a feedback effect where distant light sources become increasingly difficult to observe as their recession velocities approach and eventually exceed the speed of light itself. The wavelength stretching affects different colors of starlight in proportion to their original frequencies. Blue light from distant sources experiences more severe energy loss than red light from the same objects because higher frequency radiation suffers greater percentage changes when stretched to longer wavelengths. This differential redshift effect preferentially removes the shortest wavelengths from distant starlight, leaving only the longest wavelengths visible while pushing most stellar radiation beyond the detection threshold. The galaxy GNZ11, one of the most distant galaxies ever observed, illustrates how cosmic expansion steals light from astronomical objects. This galaxy emits light that has been redshifted by a factor of approximately 11, meaning that ultraviolet radiation originally emitted by hot young stars now arrives at Earth as infrared light with 11 times longer wavelengths and correspondingly reduced energy content. The original brightness of those stellar sources has been severely diminished by this cosmic stretching process. Future projections indicate that cosmic expansion will continue removing distant light sources from our observable universe. Galaxies currently visible will gradually fade from view as their recession velocities increase due to accelerating expansion. Eventually, these distant stellar systems will cross the cosmic horizon where their recession speeds exceed light velocity, making them permanently invisible regardless of their actual brightness or stellar content. Cosmic expansion ensures that the universe will become progressively darker over time rather than brighter. As space continues expanding at accelerating rates, an increasing fraction of stellar light will be redshifted beyond visible wavelengths. The night sky that appears dark to us today represents the brightest it will ever be, as future cosmic expansion will remove more and more distant light sources from our observable environment. Modern measurements show that cosmic expansion removes approximately 10% of the light energy from galaxies located 1 billion light-years away. This percentage increases dramatically for more distant objects, with galaxies at redshift values of 2 or higher losing more than 75% of their original luminous energy to wavelength stretching. The cumulative effect across all cosmic distances ensures that expansion acts as a cosmic dimmer switch that continuously reduces the total amount of visible starlight reaching any observation point in the universe. Yet even as cosmic expansion steals visible light from distant sources, it reveals something extraordinary about the universe itself. Hidden within the apparent darkness lies evidence of ancient illumination that once filled all of space with brilliant radiance, now transformed into invisible wavelengths that surround us at every moment. The invisible cosmic microwave background. This radiation permeates every cubic centimeter of space around us, carrying the afterglow of the most violent event in cosmic history. At this very moment, your body encounters approximately 400 photons per cubic centimeter of ancient light that originated during the Big Bang itself, filling every corner of the observable universe with electromagnetic energy that has been traveling through space for nearly 13.8 billion years. The cosmic microwave background represents the oldest light detectable in the universe, providing direct evidence of conditions that existed when the cosmos first became transparent to radiation. This ancient radiation maintains a nearly perfect, uniform distribution throughout all of space, creating an invisible glow that permeates the entire cosmic environment. The background fills the universe with approximately 410 million photons per cubic meter, carrying energy that originated when the universe was only 380,000 years old. During that primordial epoch, the cosmos had cooled sufficiently for electrons and protons to combine into neutral hydrogen atoms, allowing electromagnetic radiation to travel freely through space for the first time in cosmic history. When this background radiation first began its journey through the universe, it possessed characteristics dramatically different from what we observe today. The primordial light originated as intense, visible, and infrared radiation with temperatures exceeding 3000 Kelvin, creating conditions bright enough to illuminate the entire cosmic volume. This ancient glow carried tremendous energy densities that would have made the early universe appear brilliantly luminous to any hypothetical observer present during that remote epoch. Cosmic expansion has stretched these ancient photons across nearly 14 billion years of universal growth, transforming their original visible wavelengths into microwave radiation completely invisible to human perception. The expansion process has increased the wavelengths of this primordial light by a factor of approximately 1,100, shifting radiation that once appeared as bright orange and red illumination into microwave frequencies with wavelengths measuring several millimeters. This wavelength stretching has simultaneously reduced the energy content of individual photons by the same factor, dramatically cooling the ancient radiation. The current temperature of the cosmic microwave background measures approximately 2.725 Kelvin above absolute zero, representing the cooled remnant of the universe's primordial fireball. This frigid temperature corresponds to peak emission wavelengths in the microwave spectrum, far beyond the sensitivity range of human vision. The radiation maintains this uniform temperature across the entire observable universe with variations smaller than 1 part in 100,000, demonstrating the remarkable homogeneity of conditions during the early cosmic era. Recent measurements from advanced space-based instruments have refined our understanding of the cosmic microwave background's detailed properties and subtle variations. The Planck satellite mission completed comprehensive mapping of temperature fluctuations across the entire sky, revealing patterns that encode information about the universe's geometry, composition, and evolutionary history. These measurements show that the background radiation provides precise constraints on cosmic composition, revealing the relative amounts of ordinary matter, and dark energy that fill the universe. The discovery of polarization patterns within the cosmic microwave background has revealed additional layers of information about the universe's earliest moments. These polarization signatures preserve evidence of gravitational waves that propagated through the primordial plasma, potentially offering glimpses of cosmic inflation processes that occurred during the first fraction of a second after the Big Bang. Analysis of these polarization data has provided new insights into the fundamental physics governing the universe's birth and initial expansion. Specialized microwave telescopes and radio astronomy facilities detect this invisible cosmic illumination through sophisticated receiver systems cooled to temperatures near absolute zero. These instruments measure the faint microwave signals against carefully calibrated reference sources, allowing astronomers to map the intensity and polarization characteristics of the background radiation across different regions of sky. The detection process requires extraordinary sensitivity because the cosmic microwave background carries only billionths of a watt per square meter of collecting area. The cosmic microwave background provided crucial evidence that resolved significant aspects of the darkness paradox by demonstrating that the universe was indeed brilliantly bright during its early history. This discovery proved that the cosmos once contained the uniform illumination that early astronomers predicted should exist, but showed how cosmic evolution and expansion had transformed that ancient brightness into invisible microwave radiation. The background glow represents the missing light that should theoretically brighten the night sky according to simple stellar counting arguments. Ground-based radio telescopes detect the cosmic microwave background as a persistent signal that appears identical regardless of observing direction or time of year. This omnipresent radiation creates a baseline noise level in radio astronomy observations, requiring sophisticated calibration techniques to separate cosmic signals from terrestrial interference sources. The uniformity of this background across all directions provides compelling evidence for the cosmological principle that assumes the universe appears the same from all vantage points on large scales. Measurements of the cosmic microwave background spectrum show nearly perfect agreement with theoretical blackbody radiation curves, confirming that this ancient light originated from thermal equilibrium conditions in the early universe. The spectrum peaks at frequencies near 160 gigahertz with wavelengths around 1.9 millimeters, characteristics that match predictions for cooled blackbody radiation that has been redshifted by cosmic expansion. The existence of cosmic microwave background radiation demonstrates that space actually glows with ancient light carrying tremendous total energy content despite remaining invisible to human perception. This hidden illumination fills the universe with approximately 400 million photons per cubic meter, creating energy densities that exceed the contribution from all visible starlight combined. The darkness we perceive results not from the absence of cosmic illumination, but from our inability to detect the dominant form of electromagnetic radiation that surrounds us. Yet even this ancient glow represents only part of the cosmic illumination story, as stellar light itself faces additional obstacles during its journey across the vast expanses of space. Between these galaxies lie a complex network of gas clouds, dust particles, and molecular structures that intercepts and absorbs enormous quantities of starlight during its billion-year journey through space. This intergalactic medium creates a cosmic filtering system that removes substantial amounts of illumination from the night sky, contributing significantly to the darkness that surrounds us, despite countless luminous stellar sources scattered throughout the universe. The intergalactic medium consists primarily of hydrogen and helium gases distributed throughout the space between galaxy clusters. These gases exist in extremely low densities compared to planetary atmospheres, yet their cumulative effect across billions of light years becomes substantial. Individual hydrogen atoms scattered throughout intergalactic space absorb specific wavelengths of starlight, particularly ultraviolet radiation that matches the energy required to ionize hydrogen atoms. This selective absorption removes high-energy photons from stellar radiation, reducing the total amount of light that successfully completes its cosmic journey. Cosmic dust represents an even more effective light-blocking mechanism than gas absorption. These microscopic particles consist of silicate materials, carbon compounds, and ice crystals that formed in the atmospheres of dying stars and were subsequently expelled into interstellar space. Dust grains typically measure between 0.1 and 1 micrometers in diameter, making them similar in size to the wavelengths of visible light. This size relationship allows dust particles to interact very efficiently with electromagnetic radiation through both absorption and scattering processes. The absorption efficiency of cosmic dust varies dramatically depending on the wavelength of incident light. Blue and ultraviolet wavelengths experience much stronger absorption than red and infrared radiation, causing distant starlight to appear redder and dimmer than it would in the absence of dust interference. This preferential absorption of shorter wavelengths means that dust clouds can completely eliminate blue light from distant sources while allowing red light to pass through with reduced intensity. Recent observations have revealed previously unknown absorption mechanisms operating within the intergalactic medium. Advanced spectroscopic surveys have identified complex molecular structures that absorb light at specific frequencies, creating absorption lines that were not predicted by earlier theoretical models. These molecules include various carbon-based compounds and metallic species that were ejected from galaxies through stellar winds and supernova explosions. The discovery of these additional absorption processes indicates that the intergalactic medium removes even more starlight than astronomers previously calculated. The distribution of absorbing material varies significantly across different regions of the universe. Some directions in space contain relatively clear sightlines with minimal dust and gas interference, allowing distant galaxies to appear brighter and more easily detectable. Other regions contain dense concentrations of absorbing material that can reduce the brightness of background objects by factors of hundreds or thousands. This patchy distribution creates a complex pattern of cosmic visibility where some stellar populations remain completely hidden behind dust clouds. The zone of avoidance represents a region of sky where dust within our own galaxy blocks our view of external galaxies located in that direction. This dust lane obscures approximately 20% of the observable universe from optical telescopes, hiding millions of galaxies that would otherwise contribute to the cosmic light background. Similar absorption effects occur on intergalactic scales, where dust expelled from galaxies creates shadowing regions that block light from more distant sources. Recent infrared observations have revealed hidden galaxies that were completely obscured by dust clouds in visible light surveys. These discoveries indicated that previous galaxy counts had significantly underestimated the total stellar content of the universe because dust clouds blocked substantial numbers of luminous objects from detection. The wavelength dependence of cosmic absorption creates systematic biases in astronomical observations, with surveys conducted at different wavelengths revealing different populations of cosmic objects. Gravitational interactions between galaxies can enhance dust absorption by concentrating absorbing material into dense clouds. When galaxies collide or undergo close encounters, their gravitational forces can compress interstellar dust into regions with much higher densities than typical intergalactic values. These compressed dust clouds create particularly effective light-blocking barriers that can completely obscure entire galaxy clusters from certain viewing angles. The cumulative effect of cosmic absorption operates over vast distance scales throughout the observable universe. Light from the most distant galaxies must traverse billions of light years of intergalactic medium, encountering countless absorption opportunities during its journey. Even if individual absorption events remove only small fractions of the total light, the accumulated effect across cosmic distances can substantially reduce the brightness of extremely distant sources. Magnetic fields within the intergalactic medium also contribute to light absorption through processes involving charged particles and plasma interactions. These magnetic effects can deflect and absorb certain wavelengths of electromagnetic radiation, adding another layer of complexity to the cosmic absorption picture. Recent studies of magnetic field absorption have revealed that these processes remove additional starlight beyond the amounts predicted by gas and dust absorption alone. The absorption mechanisms operating within intergalactic space ensure that substantial quantities of stellar illumination never reach Earth to contribute to night sky brightness. Yet these visible obstacles represent only part of the cosmic architecture that shapes how light travels through the universe, as invisible forces far more massive than all the gas and dust combined exert their own profound influence on the distribution of cosmic illumination. Dark matter's influence on cosmic structure. Dark matter comprises approximately 85% of the universe's total mass, creating an enormous three-dimensional network that spans the entire observable universe. This invisible substance interacts with ordinary matter only through gravitational attraction, yet it controls where every star and galaxy can exist throughout the cosmos. The cosmic architecture formed by dark matter determines precisely where light sources can form and how their illumination propagates through space. The gravitational influence of dark matter shapes cosmic structure through a process that began shortly after the Big Bang, when tiny density fluctuations in the primordial universe began growing under gravitational attraction. Dark matter particles, being immune to electromagnetic forces, could collapse into increasingly dense concentrations while ordinary matter remained dispersed in hot plasma. These early dark matter condensations created gravitational wells that eventually attracted gas and dust, providing the seeds around which the first stars and galaxies would later form. Recent research has revealed the intricate details of how dark matter constructs the cosmic web through sophisticated computer simulations that track billions of particles across cosmic time. These calculations show that dark matter forms an interconnected network of filamentary structures spanning millions of light years, with dense nodes occurring at intersection points where multiple filaments converge. The cosmic web acts as a scaffolding that channels ordinary matter along predetermined pathways, concentrating star-forming material into specific locations while leaving vast regions nearly empty of luminous objects. These filamentary structures create enormous voids between galaxy clusters where virtually no stars exist to contribute illumination. The largest cosmic voids span hundreds of millions of light years in diameter, containing density levels less than 10% of the cosmic average. Within these supervoids, galaxy densities drop to nearly zero, creating regions of space where starlight sources become separated by distances so vast that their combined illumination cannot brighten the intervening darkness. Dark matter's gravitational clustering explains why visible matter concentrates into galaxies rather than spreading uniformly throughout space. Without dark matter's attractive influence, the ordinary matter that forms stars would remain evenly distributed across cosmic volumes, potentially creating the uniform stellar distribution that early astronomers assumed must exist. Instead, dark matter's gravitational effects gather star-forming material into dense concentrations, leaving enormous empty regions between these stellar accumulations. Studies of cosmic web formation have identified how dark matter creates what astronomers describe as a lumpy universe where matter distribution varies dramatically across different scales. Computer models tracking dark matter evolution show that gravitational instabilities amplify small initial density variations into the dramatic contrast observed today. Regions that began with slightly higher dark matter concentrations grew into massive galaxy clusters, while areas with lower initial densities became increasingly empty as material drained away toward denser regions. This cosmic lumpiness directly affects our perception of universe brightness by concentrating light sources into specific locations while creating vast dark zones between them. If dark matter distributed ordinary matter uniformly throughout space, every direction in the night sky would contain similar numbers of stars at various distances. Instead, dark matter's gravitational architecture creates dramatic variations in stellar density, with some directions showing rich galaxy clusters while others reveal nearly empty voids, stretching across hundreds of millions of light years. Gravitational lensing effects caused by dark matter concentrations further influence how starlight reaches Earth by bending and redirecting photon paths through curved space-time. Massive dark matter structures create gravitational fields strong enough to deflect light rays, causing distant galaxies to appear distorted, magnified, or displaced from their actual positions. These lensing effects can focus light from background sources, making some objects appear brighter than expected, while simultaneously creating shadow zones where light gets deflected away from potential observers. Large-scale surveys mapping dark matter distribution have revealed how this invisible architecture creates systematic patterns in cosmic illumination. Cosmic Webb surveys show that approximately 50% of cosmic volume consists of voids containing less than 20% of average matter density. These underdense regions contribute minimal starlight to the cosmic background, while the remaining matter concentrates into filaments and nodes that produce bright but isolated sources of illumination. Dark matter's influence extends to individual galaxy formation processes that determine how efficiently ordinary matter converts into luminous stars. The gravitational potential wells created by dark matter halos control how gas flows into galaxies and regulate star formation rates through complex feedback mechanisms. Galaxies forming within more massive dark matter halos tend to contain larger stellar populations, while those in smaller halos remain dim or fail to form stars altogether. The cosmic web structure ensures that most of space remains permanently dark by preventing uniform star distribution across cosmic volumes. Dark matter filaments channel star, forming material along specific pathways, creating highways of galaxy formation that connect dense nodes while bypassing enormous empty regions. This channeling effect concentrates available luminous matter into narrow corridors, leaving the majority of cosmic volume virtually devoid of light sources. Computer simulations tracking cosmic evolution over billions of years show that dark matter's architectural influence strengthens over time as gravitational clustering continues. The contrast between dense and empty regions increases as matter continues flowing from voids into filaments and nodes. This ongoing concentration process creates an increasingly sparse network where luminous objects cluster into isolated regions separated by vast empty zones, maintaining the characteristic darkness that dominates the universal environment. Yet this current cosmic architecture represents only a snapshot of an evolving system whose illumination patterns will undergo dramatic changes as the universe continues aging through deep time. The future of cosmic darkness. These evolutionary timelines reveal the universe's inevitable trajectory toward complete darkness. Rather than growing brighter over time, space faces an inescapable march toward eternal night. Every star currently illuminating the cosmos represents a temporary beacon that will eventually exhaust its nuclear fuel and fade into obscurity, leaving behind only cold remnants scattered throughout an ever-expanding void. Stellar evolution operates according to strict physical laws that govern how long different types of stars can sustain their luminous output. The most massive stars burn through their nuclear fuel at prodigious rates, converting hydrogen into heavier elements through fusion reactions that generate tremendous energy. These stellar giants, despite their impressive brightness, maintain their luminosity for only millions of years, before exhausting their fuel reserves and exploding as supernovae. The resulting neutron stars and black holes contribute no visible light to the cosmic environment, removing these once brilliant sources from the stellar inventory. Medium-sized stars like our Sun follow more conservative energy budgets that allow them to shine for billions of years. Current calculations indicate that solar-type stars can maintain hydrogen fusion for approximately 10 billion years before transitioning into red giant phases. During these evolved states, stars expand to enormous sizes while gradually cooling and dimming. Eventually, these aging stars shed their outer atmospheres to form planetary nebulae, leaving behind white dwarf remnants that slowly cool over trillions of years until they become invisible black dwarfs. The smallest stars in the universe, known as red dwarfs, represent the most economical users of nuclear fuel in the cosmic population. These dim stellar objects burn hydrogen so slowly that they can maintain fusion reactions for hundreds of billions or even trillions of years. Red dwarfs will outlive all other stellar types by enormous margins, continuing to provide faint illumination long after massive stars have exploded and sun-like stars have evolved into white dwarfs. However, even these stellar misers must eventually exhaust their fuel supplies and fade into darkness. The timeline for cosmic dimming spans scales that dwarf human comprehension. Within the next 100 billion years, star formation will essentially cease throughout most of the universe as galaxies exhaust their supplies of gas and dust needed to create new stellar objects. The Milky Way will merge with the Andromeda Galaxy during this period, triggering a final burst of star formation before the combined system settles into a configuration where no new stars can form. This represents the closing of the stellar nurseries that have produced luminous objects throughout cosmic history. By 1 trillion years in the future, most sun-like stars will have evolved beyond their main sequence phases and entered their final cooling stages as white dwarfs. The night sky will contain far fewer bright stars than exist today, with only the longest-lived red dwarfs continuing to provide modest amounts of visible light. Galaxy collisions and gravitational interactions will scatter many stellar remnants into intergalactic space, further reducing the density of light sources available to illuminate cosmic darkness. Recent 2025 predictions incorporating data from the James Webb Space Telescope have refined our understanding of this cosmic cooling timeline. Webb's observations of early galaxy formation suggest that star formation peaked earlier in cosmic history than previously thought, meaning the universe has already passed through its brightest epoch. Current stellar populations represent the dimming remnants of more vigorous star formation processes that operated when the cosmos was younger and contained more readily available fuel for stellar nucleosynthesis. Cosmic expansion accelerates this dimming process by stretching the wavelengths of starlight and increasing the distances between luminous objects. As space continues expanding at ever-increasing rates, the light from distant galaxies will be redshifted beyond visible wavelengths while their recession velocities carry them beyond observable horizons. Dark energy drives this acceleration, representing approximately 68% of the universe's total energy content and overwhelming the gravitational attraction that might otherwise halt cosmic growth. The heat death scenario represents the ultimate fate awaiting our expanding universe, according to current cosmological understanding. As cosmic expansion continues under dark energy's influence, the average temperature throughout space will approach absolute zero. Thermal equilibrium will eventually distribute all available energy evenly across infinite volumes, eliminating the temperature differences needed to sustain any form of organized activity. This final state represents maximum entropy, where no further changes can occur within the cosmic system. Current observations reveal that we inhabit the universe during its brief period of maximum illumination before the long descent into permanent darkness begins. The stellar formation rate peaked approximately 10 billion years ago when the cosmos contained abundant gas supplies needed to fuel massive star formation episodes. Since that time, stellar birth rates have declined steadily as galaxies consume their available fuel without sufficient replenishment to maintain previous production levels. The profound realization emerges that cosmic darkness represents the natural and permanent state of the universe, interrupted only briefly by the temporary phenomenon of stellar nucleosynthesis. The current epoch of cosmic illumination spans perhaps 100 billion years within a universe destined to exist for timescales exceeding 10 to the power of 100 years. We witness the universe during its fleeting moment of brightness before eternal darkness reclaims the cosmos, making every photon of starlight a precious reminder of the temporary nature of cosmic illumination. This sobering truth about our universe's destiny transforms how we understand the darkness that surrounds us each night. The profound implications of cosmic darkness extend far beyond academic astronomy into fundamental questions about our place within an evolving universe. Every aspect of this darkness tells the same story about a cosmos that began 13.8 billion years ago and races toward an inevitable future of eternal cold emptiness. Tonight, when you look up at the stars, remember that you witnessed the universe during its brief moment of maximum brightness before accelerating expansion and stellar death claim every source of light. The darkness between those distant suns represents not empty space, but the universe's true nature, young, expanding, and temporary in its current luminous state.